Hello everyone, welcome to the lecture. Myself Devananda Rao, working as Associate Professor in the Department of CSC, MLR Institute of Technology, Hyderabad. Today's topic is code optimization. So, principal sources of optimization. Principal sources of optimization. What is principal sources of optimization? A transformation of a program is called local if it can be performed by looking only at the statements in a basic block. So, if you perform the transformations on the within the basic block, that is local, otherwise it is called global. Many transformations can be performed at both the level, that is local and global levels. Local transformations are usually performed first. We have four types of function preserving transformations. Function preserving transformations, that is, there are a number of ways in which a compiler can improve a program without changing the function it computes. Without changing the meaning of the program, we can improve the program by using these four techniques. The result should not be changed, the program function should not be changed. Without changing the program functionality, we can improve the program code by using one of the four functions, techniques, transformations. First one is common sub-expression elimination, copy propagation, dead code elimination and constant folding. These are the common examples of such function preserving transformations. Common sub-expression elimination, first type. An occurrence of an expression E is called common sub-expression if E was previously computed and the values of variables in E have not been changed since the previous computation. We can avoid recomputing the expression if we can use the previously computed value. Here, after the previously computation of expression, if the variables of expression is not changed, we can reuse the same result. No need to recompute the expression in further basic blocks. For example, here we have 6 statements, intermediate, that is the 3 address statements. T1 is equals to 4 into I, T2 is equals to A of T1, T3 is equals to 4 into J, T4 is equals to 4 into I, T5 is equals to N, T6 is equal to B of T4 plus T5. It is a 3 address code. Here the first statement and fourth statement computing the same expressions, that is 4 into I. Between first statement and second statement, the variable I is not modified, not updated. See, second statement T2, there is no I variable, T3 there is no I variable. So, I is not modified, not updated. So, that this first and fourth statements are computing same expression. So, that expression is common sub-expression. Common sub-expression. So, that we can eliminate the common sub-expression to optimize the intermediate code. The above code can be optimized using the common sub-expression elimination. See, T1 is equals to 4 into I, T2 is equals to A of T1, T3 is equal to 4 into J, T5 is equals to N. So, T4 is eliminated because that statement is common sub-expression, containing common sub-expression. T6 is equal to B of T1 plus T5. The common sub-expressions T4 is equals to 4 into I is eliminated as its computation is already in T1. See, T1 is equals to 4 into I. The result of 4 into I is stored in T1. So, that we can reuse that result of T1 wherever required. No need to recompute the 4 into I in coming subsequent basic blocks. And value of I is not being changed from definition to use. So, from first statement to fourth statement, I is not modified. This is common sub-expression elimination. Next, copy propagation. Assignments of the form F is equals to G is called copy statement or copies for short. Copy, that is, in the 3 address statements basic block, if the copy statement occurs, F is equals to G, that is value of G is assigned to F. So, afterwards, after doing this copying G to F, we can use G for instead of F in the subsequent basic blocks. See, use G for F whenever possible after copy statement. after this statement in the program f is equals to g, we can use g instead of f wherever possible. Copy propagation means use of one variable instead of another. So, using variable g instead of f. This may not appear to be an improvement of the code, but as we shall see, it gives us an opportunity to eliminate variable x. For example, x is equals to pi is a variable, copy statement, x is equals to pi is assigned to x. After some statements, we have another expression, computation, a is equals to x into r into r, x into r into r. The optimization using copy propagation can be done as follows, so that we can eliminate variable e by rewriting this a is equals to pi into r into r, pi into r into r. So, we have eliminated variable x by using pi is used instead of x. That is the advantage of copy propagation. So, that we can use wherever possible, we can use copy propagation. Copy propagation means using one variable instead of another variable. Here variable x is eliminated. Next one, dead code elimination. A variable is live at a point in a program if its value can be used subsequently, otherwise it is dead at that point. For example, here I is initialized to 0. If I is equals to 1, this block of statements will be executed, otherwise control goes to next statement. But here the if statement is dead code statement, because the condition will never get satisfied. Why? Because I value is 0, initialized to 0, I will not be changed. So, if I is equal to 1 only, the body of the statement will be executed. The statement now f is a statement that is dead code. Because of this condition, this program will never get satisfied, will never get executed. So, that dead code elimination. We have to eliminate this dead code if statement in the program to improve the code. Next, constant folding. If the value of an expression is constant and use the constant instead of expression. For example, a is equals to 3.1457 by 2. Here the division operation is performed in the expression computation. So, that this is a constant expression, it is a constant expression. If you compute this expression during compile time, we can directly use that value. What is 3.14 by 2 by 1457 by 2, that is 1.570. So, that we can assign directly a is equals to 1.570, thereby eliminating a division operation. So, division operation will take more time for computation. So, instead of using divisions for constant expressions, we can directly use the result, that is constant folding. Next, loop optimization. The inner loops where the programs tend to spend the bulk of time, that is most of the time during execution, the program will spend most of the time in computing the loops. That is, our aim is, if we reduce the number of statements within the loop, we can reduce the execution time. So, the running time of a program may be improved if we decrease the number of instructions in an inner loop, even if you increase the amount of code outside the loop. If you write any number of instructions outside the loop, that will take less number of time, less time for execution. If you write more instructions within the loop, it will take more time for execution. So, our aim is to reduce the number of statements within the loop, so that the execution time will be improved. So, there are techniques to improve the loop optimization. First one is code motion, another is reduction in strength. Code motion is which moves code outside a loop. Reduction in strength means which replaces an expensive operation by a cheaper one, such as multiplication by addition. Wherever possible, we can replace multiplication operation by addition operation. Multiplication will take more time than addition. So, code motion means which moves the code outside a loop. Next, code motion decreases the amount of code in a loop is called code motion. This transformation takes an expression that yields the same result independent of the number of times a loop is executed and places the expression before the loop. Here we can move the code from the loop, inner loop, to the outside the loop, that is code motion. When we move the code from inner loop to outer loop, that means if any number of times the loop is executed, the value of the expression, if not changed, if the value of the expression is not changed for any number of times the loop is executed, that is called loop invariant computation. That is called loop invariant computation. At that time, we can move that statement to outside of the loop. While I less than or equals to limit 2. Here, limit minus 2 is there in the loop, so that using code motion technique, we can move this expression outside the loop. That is, code motion will result in the equivalent of the form. See this, we can store the result of limit minus 2, we can store the result of limit minus 2 to variable t. So that t is equals to limit minus 2, that is the statement outside the loop. Now, in the loop, while I less than or equals to t. So, instead of using limit minus 2 in the loop, we can use directly a temporary variable t, so that it will take less time to execution. So, most of the instructions are moved to the outside the loop wherever possible, if it is a loop invariant computation. Loop invariant computation means expression that yields the same result independent of the number of times a loop is executed. Next, reduction in strength. Reduction in strength replaces expensive operations by equivalent and cheaper ones on the target machine. For example, x square is invariably cheaper to implement as x star x. For example, x square is invariably cheaper to implement as x star x than as a call to an exponentiation routine. So, exponentiation will take more time than this multiplication. Then, fixed point multiplication or division by power of 2 is cheaper to implement as a shift operation. So, shift operation will take more time for fixed point multiplication or division. Floating point division by a constant can be implemented as multiplication by a constant, which may be cheaper. Thank you.